We see the universe with our eyes, but its deepest architecture remains completely invisible. That hidden scaffolding controls galaxies, shapes space-time, and may hold the final secrets of reality. By the end of this journey, you will have explored 30 of the most mind-bending theories about what lies beneath the surface of everything from the cosmic web to quantum foam, from dark matter halos to the possibility that we live inside a simulation. What really holds the cosmos together? What strange structures are we only beginning to glimpse? Come with me as we map the unseen blueprint of existence. What do you think the universe is truly made of? The largest known structure in the universe is not a galaxy or a cluster but a web. Across billions of light years, galaxies are not scattered randomly. They are strung together along vast filaments of invisible matter, like beads on an unimaginably enormous thread. These filaments form the cosmic web, the skeleton of everything we see. Simulations and surveys, such as the Sloan Digital Sky Survey, have mapped this network in stunning detail. What they reveal is a pattern of dense nodes where filaments cross, holding massive galaxy clusters and vast empty voids between them. The filaments themselves are mostly dark matter, the mysterious substance that neither emits nor reflects light. Ordinary gas and galaxies follow these threads, pulled by gravity along paths set long ago. The cosmic web dictates how galaxies form, how they move, and how they cluster. It is the hidden framework that shapes the universe on its largest scales. Yet even this immense network is only the outermost layer of a far deeper structure. What lies beneath the cosmic web, inside the nodes and along the threads, hints at even stranger arrangements of space and time. Every galaxy, including our own Milky Way, is trapped inside an enormous invisible sphere. Astronomers call it a dark matter halo. This halo stretches far beyond the visible stars and gas, sometimes reaching hundreds of thousands of light years across. It is made of dark matter, the mysterious substance that does not emit, absorb, or reflect any light. We cannot see it directly, but we know it is there because of how it yanks on the things we can see. The first clue came from galactic rotation curves. In the 1970s, astronomer Vera Rubin measured how fast stars orbit the center of spiral galaxies. According to Newton's laws, stars farther from the center should move slower, just like planets farther from the sun, but Rubin found something strange. The outer stars were moving just as fast as the inner ones. That should have flung them out of the galaxy unless something extra, something invisible, was holding them in place. That extra mass is the dark matter halo. It acts like an enormous gravitational glue, keeping the spinning galaxy from tearing apart. The second piece of evidence comes from gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light like a magnifying glass. By studying how the light bends, astronomers can map the mass that caused the bending. And time and again, they find far more mass than the visible stars and gas can account for. The extra mass is the dark matter halo. In some cases, the lensing reveals that halos are not perfect, smooth spheres. They have clumps and lumps, substructures called subhalos. These smaller clumps of dark matter can host their own tiny galaxies, the faint dwarf galaxies that orbit larger ones. Our own Milky Way has dozens of these dwarf companions, each one a little clue about the clumpiness of the halo. This raises a deep mystery. What is dark matter actually made of? The leading idea is that it consists of a new type of particle, one that interacts only through gravity and the weak nuclear force. Experiments deep underground are trying to catch a faint signal from such particles passing through Earth. So far, nothing. The particle remains hidden, and the substructures within halos may be the key. If dark matter interacts with itself even a tiny bit, those interactions could shape the subhalos in ways we can measure. How exactly do these invisible spheres nudge the visible universe around them? That question leads directly to the next hidden structure, the way dark matter halos and ordinary matter collide and dance together across cosmic time. Between the dense clusters and along the dark matter threads, the cosmic web stretches across hundreds of millions of light years. But what lies in the enormous empty spaces in between? Those are the voids, and they are far more interesting than their name suggests. For decades, astronomers thought voids were simply regions of space with almost nothing in them, vast deserts where galaxies rarely formed. But deeper surveys have revealed a different story. Voids are not truly empty. They contain faint dwarf galaxies, so dim and sparse that they barely register in our telescopes. And they hold diffuse gas, thin strands of hydrogen that have not yet collapsed into stars. This gas is so spread out that it emits almost no light, making it a ghostly presence. Yet it is there, and it plays a key role in how the universe expands. The filaments that bridge galaxy clusters are the opposite of voids. They are the dense, thread-like highways along which galaxies flow, pulled by gravity into the clusters. These filaments are made of dark matter and ordinary gas, and they can stretch for hundreds of millions of light years. Imagine a spiderweb where the silk threads are made of invisible matter and the dewdrops are the galaxies. That is the cosmic web. The voids are the gaps between those threads, the huge bubbles where matter has been pushed out over billions of years by the relentless expansion of space. Because voids are so empty, they act as natural laboratories for studying dark energy. Dark energy is the mysterious force that is accelerating the expansion of the universe. In dense regions like galaxy clusters, gravity fights against this expansion. But inside a void, the pull of gravity is much weaker. That means dark energy's effect is more pronounced. By measuring how voids grow and change over time, astronomers can test different models of dark energy. Some voids are expanding faster than others, and that pattern holds clues about the nature of this repulsive force. It is like using a vacuum chamber to study the behavior of a gas. Remove the clutter, and you see the underlying process. The faint dwarf galaxies inside voids are especially valuable. They formed in isolation with very little interference from larger neighbors. That means they preserve a pristine record of the early universe, almost like fossils. Studying their chemistry and motion tells us about the conditions just after the Big Bang. And the diffuse gas inside voids, though nearly undetectable, can be observed using the faint absorption lines it leaves in the light of distant quasars. Those measurements reveal the composition and temperature of the intergalactic medium, the material that fills the space between galaxies, so the voids are not just empty. They are the quiet, dark corners of the cosmos where the battle between gravity and dark energy plays out most clearly. And that battle shapes the entire large-scale structure of the universe. The way galaxies cluster, the way filaments stretch, and the way voids swell are all determined by the balance of these two forces. What exactly is dark energy, and how does it fit into the hidden scaffolding of reality? That is the next piece of the puzzle, and it leads to one of the most startling theories about the universe's ultimate fate. The universe is not just expanding, it is accelerating. That discovery, made in the late 1990s by two independent teams studying distant supernova, turned cosmology upside down. Astronomers expected the expansion to be slowing down due to gravity. Instead, they found that something was pushing everything apart faster and faster. That something is dark energy. It makes up about 68% of the total energy budget of the cosmos, yet we have no direct evidence of what it actually is. It is the most abundant and the most mysterious component of the hidden structure of reality. The simplest explanation is the cosmological constant. This idea comes directly from Einstein's equations of general relativity. He originally introduced a constant term to keep the universe static, but after the discovery of expansion, he called it his biggest blunder. Now we know he might have been right all along, just for the wrong reason. The cosmological constant represents a constant energy density that fills empty space uniformly. It does not dilute as the universe expands. Instead, it exerts a negative pressure, a kind of anti-gravity that pushes space apart. If dark energy is truly a cosmological constant, then its value is incredibly tiny, fine-tuned to an absurd degree. If it were even slightly larger, the universe would have flown apart before galaxies could form. If it were slightly smaller, gravity would have pulled everything back into a big crunch long ago. That fine-tuning is a puzzle, and it points toward a deeper explanation. Another leading theory is quintessence. Unlike the cosmological constant, quintessence is not constant. It is a dynamic field that changes over time, like an invisible fluid that evolves as the universe ages. This field has its own energy and pressure, and it can vary across space. Imagine a landscape with hills and valleys. The field rolls down these slopes, and its speed determines how strongly it pushes things apart. If quintessence is real, then dark energy was weaker in the past and will grow stronger in the future, or vice versa. This would leave a detectable signature in the way galaxies cluster and in the pattern of the cosmic microwave background. Future surveys, like those using the Euclid telescope or the Rubin Observatory, are designed to measure this. They will track how the expansion rate has changed over billions of years, looking for deviations from the simple constant model. A third possibility is that gravity itself behaves differently on the largest scales. This is known as modified gravity. Einstein's general relativity works beautifully inside the solar system, but maybe it breaks down across billions of light years. Some theories propose that gravity weakens or strengthens in ways that mimic dark energy. Others introduce extra dimensions or additional fields that alter the geometry of spacetime. Modified gravity theories are tricky to test because they often predict the same early universe as standard cosmology, but they do leave distinct fingerprints in the growth of cosmic structure. For instance, in modified gravity, the way galaxies cluster and the way voids grow can diverge from the standard model. Astronomers are using the shape of the cosmic web to look for those differences. If gravity is not what we think, then the entire hidden framework of the universe is different from our current picture. How does dark energy affect the cosmic web? It stretches the filaments and empties the voids further. Without dark energy, the filaments would have collapsed into denser, tighter threads over time. Galaxies would have merged more frequently, and the voids would have remained small and shallow. But dark energy's repulsive force fights against gravity's pull. It slows the growth of clusters and pulls the filaments apart, making them thinner and more tenuous. Meanwhile, the voids expand faster, growing into enormous bubbles of nearly empty space. This means that the large-scale structure we see today is a snapshot of a battle between two titans, gravity pulling matter together and dark energy pushing everything apart. The balance between them determines the fate of the universe. If dark energy is constant, the universe will continue accelerating forever, eventually leaving our local group of galaxies as an isolated island in a vast dark emptiness. If quintessence changes or if gravity itself evolves, the outcome could be different. The cosmic web will either be ripped apart or it might eventually slow down and reverse. These are still just the known unknowns. Dark energy hints at something even more fundamental, a hidden layer of reality that controls the expansion of space itself. That layer might connect to other exotic structures like cosmic strings or domain walls that we have not yet observed. But before we go there, we need to understand what dark energy is actually made of. Is it a property of empty space, a new field, or a sign that we need a completely new theory of gravity? The answer lies in the patterns of the cosmic web and in the tiny wrinkles of the early universe. Every measurement brings us closer to solving one of the greatest mysteries in all of science, and the solution will reveal a hidden structure far stranger than anything we have encountered so far. Some theories predict that the universe once passed through a series of violent phase transitions, like water freezing into ice. And just as ice can form cracks and flaws, spacetime itself may have been left with defects. Those defects are called cosmic strings. They are not tiny strings from string theory, but one-dimensional topological defects, incredibly thin lines of pure energy that stretch across the entire universe. Imagine a crack in the fabric of reality, thinner than a proton, yet extending for billions of light years. They carry enormous mass per unit length, so much that a single centimeter of cosmic string would weigh as much as a mountain. Their gravity warps the space around them, and that warping produces a strange effect. When light passes by a cosmic string, it gets bent in a specific way, creating double images of distant galaxies. Astronomers hunt for these double images in deep surveys, hoping to find a telltale pair that cannot be explained by a normal galaxy cluster. Cosmic strings are not static. They vibrate and oscillate at nearly the speed of light, and when they move, they produce ripples in spacetime called gravitational waves. Those waves are far stronger than the ones we detect from merging black holes. If a cosmic string exists anywhere within our observable universe, its passage would leave a faint, repeating pattern in the cosmic microwave background, the afterglow of the Big Bang. That pattern would look like a series of small, linear scars, a subtle stretching or squeezing of the ancient light along a specific direction. So far, maps from the Planck satellite have not found such scars, but they have set limits on how common and how massive cosmic strings can be. Future gravitational wave detectors like LISA will be exquisitely sensitive to the low-frequency hum produced by oscillating strings. If we detect that hum, it would confirm that the early universe underwent a phase transition at extremely high energies far beyond what particle accelerators can ever reach. And that would be a direct glimpse into conditions just after the Big Bang, when the universe was a seething soup of particles and fields. Cosmic strings are just one kind of topological defect. There could also be domain walls, two-dimensional sheets of energy that form when a symmetry breaks in different ways in different regions of space, or monopoles, point-like defects that carry a magnetic charge. Each type of defect tells us about the symmetries and forces that govern the infant universe, but they are all relics, fossils carved into the very structure of spacetime. The hunt for these hidden defects is not just about finding exotic objects. It is about testing the grand unified theories that try to merge the fundamental forces into a single framework. If those theories are correct, the universe should be crawling with such defects. The fact that we have not seen them yet is a puzzle, one that forces physicists to refine their models or look for subtler signatures. Cosmic strings, if they exist, are not just threads of energy, they are bridges to the earliest moments of creation. And beyond them, there may be even stranger structures woven into the fabric of reality itself. Domain walls are even stranger than cosmic strings. They are not one-dimensional lines but two-dimensional sheets, vast planes of pure energy that could span entire galaxies or even the observable universe. Imagine a crack in the fabric of water ice that runs along a surface instead of through a line. That is a domain wall, a thin, massive membrane that separates two different regions of space where the same physical laws behave differently. They form when a discrete symmetry breaks in the early universe. Discrete symmetries are things like flipping a particle's charge from positive to negative or swapping left and right. In the split seconds after the Big Bang, the universe was a hot, uniform soup. As it cooled, some forces settled into different states in different places. In one region, a particular symmetry might break one way. In another region, it breaks a different way. Where those two patches meet, a domain wall forms. That wall is a boundary between two vacuum states, two different lowest energy arrangements of the universe. And because each state has a different energy density, the wall itself possesses enormous energy. A domain wall the size of a galaxy would contain as much mass as millions of stars. Their gravity would bend spacetime just like any other massive object. But domain walls are not stable in the way we normally think. They have a problem. They tend to dominate the universe. If even one domain wall existed within our observable horizon, its energy density would be so high that it would overwhelm everything else, causing the universe to collapse or expand in a way we do not observe. This is called the domain wall problem. Cosmologists realized that if domain walls formed at high energies, they must have either been inflated away during a brief period of exponential expansion or they decayed early, leaving no trace. But some theories suggest that a tiny fraction of them could survive, perhaps as thin, dark sheets that drift through space almost invisibly. How would we ever detect such a thing? The main clue would be gravitational waves. When domain walls move, they stretch and distort spacetime, sending out ripples. If a wall oscillates or collapses, it produces a burst of gravitational waves with a characteristic frequency. Future detectors like LISA or pulsar timing arrays could pick up that signal. Another possibility is that a domain wall might leave a subtle imprint on the cosmic microwave background. As the wall passes through the early universe, it would have pushed or pulled matter and radiation, creating a pattern of slight temperature differences. So far, the maps from Planck satellite show no such pattern, but the search continues. The idea of domain walls leads naturally to another topological defect, magnetic monopoles. These are point-like objects that carry a single magnetic pole, either north or south, isolated from its opposite. In our everyday world, magnets always come with both poles. Cut a magnet in half and you get two smaller magnets, each with north and south. A magnetic monopole would be a particle with just one pole. Theories predicting magnetic monopoles often also predict domain walls because both arise from broken symmetries. Monopoles are equally problematic for cosmology. If they formed in the early universe, they would be so abundant that they would vastly exceed the observed density of matter. This is called the monopole problem, and it was one of the key motivations for the theory of cosmic inflation. Inflation stretches space so enormously that the density of monopoles and domain walls gets diluted to near zero. That explains why we see so few of them today, but the possibility remains that a few survived. Monopoles would be incredibly heavy, weighing as much as a grain of dust but squeezed into a volume far smaller than a proton. They would zip through matter almost without interacting, but their magnetic field would be unique. Detecting one is the holy grail for particle physics. Some experiments have searched for monopoles passing through superconducting loops, which would register a tiny jump in current. Others look for tracks in ancient mica, where a monopole might have left a trail of damage over billions of years. So far, no confirmed detection. The connection between domain walls and monopoles reminds us that the hidden structure of the universe is not just about big things like galaxies and voids. It is also about tiny relics, fossils of the forces that shaped reality at the very beginning. The walls and monopoles are ancient survivors, silent witnesses to a time when the universe was a seething, formless storm. And if we ever find one, we will hold a key to understanding how the fundamental laws of physics settled into their current arrangement, but we are not done yet. The most elusive structures of all might be even stranger, woven into the fabric of spacetime itself. A single north pole without a south has never been seen. Every magnet, from a refrigerator magnet to the Earth itself, always has two poles. Cut a magnet in half and you get two smaller magnets, each with its own north and south. But some of the most ambitious theories in physics, the grand unified theories that try to merge the strong, weak, and electromagnetic forces, predict that a particle with only one pole could exist. That particle is called a magnetic monopole. It would be a point-like object smaller than an atom, yet carrying an immense amount of mass, as much as a grain of dust compressed into a volume far smaller than a proton. And it would possess a magnetic charge, either north or south, completely isolated from its opposite. Such a particle would be a relic of the earliest moments of the universe, a fossil from a time when the fundamental forces were still one. The grand unified theories say that at extremely high energies, the three forces behaved as a single unified force. As the universe cooled and expanded, that symmetry broke and the forces separated. That breaking process could have produced topological defects, just like cracks in ice. Monopoles are one kind of defect, and they would have formed in great numbers during that phase transition. If they had formed as abundantly as simple calculations suggest, the universe would be filled with them, and their combined mass would have long ago caused the cosmos to collapse back on itself. That is the monopole problem, and it was one of the key reasons cosmologists proposed the theory of cosmic inflation. Inflation stretches space so violently that it dilutes the density of monopoles to almost nothing. That explains why we do not see them everywhere today, but a few might still exist, scattered across the vast volume of the universe like needles in a cosmic haystack. How would we ever find such a particle? One method is to look for their passage through matter. Because monopoles are so massive, they would travel at relatively low speeds, maybe a few hundred kilometers per second, and they would leave a distinctive trail of ionization as they plowed through atomic nuclei. Detectors buried deep underground, like those designed to search for dark matter or proton decay, could pick up the signal of a monopole passing through. Another approach is to watch for their effect on magnetic fields. Monopoles would interact strongly with magnetism, and if they were abundant, they would drain the energy from galactic magnetic fields. This is called the Parker bound, named after the astrophysicist Eugene Parker. He calculated that if the flux of monopoles crossing a galaxy were too high, they would extract the magnetic field energy faster than it could be replenished. Observations of the Milky Way's magnetic field set a strict limit on how many monopoles can be out there. That limit is very low, which is why no experiment has ever found one. The few candidate events reported over the decades have all been explained away by background noise or instrumental glitches. Some researchers have also looked for monopoles trapped in ancient materials. Iron ore deposits that formed billions of years ago could have captured a monopole that passed through at the right time. By exposing old rocks to strong magnetic fields, scientists try to extract any trapped monopole and detect its telltale magnetic signature. So far, nothing. The difficulty of detection only adds to the mystery. Monopoles, if they exist, are among the rarest objects in the universe. They are the last remaining witnesses to the moment when the forces of nature split apart, a moment that shaped everything that came after. They belong to a broader family of topological defects that includes cosmic strings and domain walls, each one a scar in the fabric of spacetime itself. And the hunt for any one of them is a hunt for a direct link to the very dawn of creation. The monopole problem helped shape modern cosmology, and the search continues. It is a quiet, patient search driven by the hope that one day, a single unique signal will arrive, carrying news from a time when the universe was still a single, seamless whole. At the smallest possible scale, spacetime itself may be anything but smooth. The Planck scale, a distance so tiny that it is about 100 million trillion trillionths of a centimeter, is where the familiar rules of geometry break down. At that size, the smooth fabric of space becomes a churning, frothing mess. It is a seething foam made of virtual black holes and wormholes that pop into existence and vanish in an instant. These are not the large black holes astronomers photograph. They are quantum objects born from the very uncertainty of nature, and they live for a sliver of time so brief that even light can barely cross them before they disappear. This concept is called quantum foam, and it is one of the most radical ideas about the hidden structure of reality. It comes from combining quantum mechanics, which describes the jittery behavior of particles, with general relativity, which describes gravity as the curvature of spacetime. At everyday scales, spacetime appears smooth like the surface of a calm lake, but zoom in far enough and that lake becomes a violent storm of waves and spray. The quantum foam is that storm. Empty space is not truly empty. It is filled with energy constantly fluctuating. According to the uncertainty principle, pairs of virtual particles can appear out of nothing, exist for a fleeting moment, and then annihilate each other. Most of the time, those particles are things like electrons and positrons. But when the energy is high enough, those virtual particles can bend spacetime so severely that they create tiny black holes. These black holes are microscopic, far smaller than an atom, and they evaporate almost instantly through Hawking radiation. Their brief lives warp the geometry of space around them, linking one region to another through microscopic wormholes. If quantum foam is real, then spacetime is not a smooth continuum but a grainy, granular structure like pixels on a screen. How could we ever detect something so small? That is where gamma-ray bursts come in. Gamma-ray bursts are the most energetic explosions in the universe, releasing more energy in seconds than the sun will in its entire lifetime. They occur when massive stars collapse or when neutron stars merge. The light from these bursts travels across billions of light years to reach us. On that long journey, it interacts with the quantum foam. If spacetime is grainy at the Planck scale, then photons of different energies might travel at slightly different speeds. High-energy photons should be delayed compared to low-energy ones, as if the froth were slowing them down. Astronomers have used the Fermi Gamma-Ray Space Telescope to compare arrival times of gamma-ray photons from distant bursts. So far, the results are inconclusive. Some observations hint at a tiny delay, but the data is not strong enough to confirm the effect. Another approach uses laser interferometry. These devices split a beam of light, send it down two perpendicular paths, and then recombine it to look for tiny changes in the lengths of those paths. If quantum foam exists, it would cause the two paths to fluctuate randomly, introducing a slight jitter in the interference pattern. The most sensitive interferometers, like LIGO, are searching for gravitational waves and are already approaching the precision needed to test quantum foam. But they have not yet seen the expected noise signature. That is either because the foam is weaker than predicted or because we need even more sensitive instruments. The idea of quantum foam connects directly to the next hidden layer, extra dimensions. Many theories, especially string theory, propose that spacetime has more than the three spatial dimensions we experience. Those extra dimensions would be curled up so small that we cannot see them directly. But quantum foam provides a possible way to probe them. If extra dimensions exist, the Planck scale might be lower than we think, making the foam more pronounced and easier to detect. That is why experiments searching for quantum foam are also tests for extra dimensions. They are looking for the same kind of spacetime granularity that would arise if the universe had hidden folds. For now, the foam remains theoretical, a prediction that has not yet been confirmed. But the search continues, using the most violent explosions in the cosmos and the most sensitive instruments ever built. Someday, a single gamma-ray burst or a perfectly calibrated interferometer might reveal that the fabric of reality is not a smooth sheet but a churning, microscopic froth of warped space and time. And that discovery would open the door to a universe far stranger than we ever imagined. What if space has more than three dimensions? It sounds like science fiction, but some of the most promising theories in physics predict exactly that. String theory, for instance, requires 6 or 7 extra spatial dimensions beyond the familiar height, width, and depth. And brane cosmology takes that idea even further, suggesting that our entire universe might be just a 3-dimensional island floating in a higher dimensional sea. If these extra dimensions exist, why have we never seen them? The answer lies in how they might be hidden. One possibility is that they are compactified, meaning they are curled up so incredibly tiny that we cannot perceive them directly. Think of a garden hose seen from a distance. It looks like a one-dimensional line, but when you zoom in, you see its second dimension, the circular cross-section coiled around itself. In the same way, extra dimensions could be wound up at the Planck scale, so small that even our most powerful microscopes cannot resolve them. That is why we only experience 3 large, extended dimensions. Another way to hide extra dimensions is through warping. In the Randall-Sundrum model, the extra dimension is not curled up but stretched and bent by gravity. Our universe sits on a 3-dimensional brane within that warped space. The warping causes most particles and forces except gravity to be confined to our brane. Gravity itself can leak into the extra dimension, which would explain why it is so much weaker than the other fundamental forces. This is a long-standing puzzle. Gravity is about 10,000 billion times feebler than electromagnetism. A warped extra dimension offers a natural explanation. If extra dimensions exist, they should leave detectable signatures. One possibility is the production of mini black holes in particle colliders. At high enough energies, 2 colliding particles could get close enough to form a tiny black hole that would quickly evaporate, leaving a distinctive spray of particles. Experiments at the Large Hadron Collider have searched for these events but found nothing so far. That sets limits on the size and number of extra dimensions. Another signature would be deviations in the law of gravity at very small scales. On human scales, gravity follows the familiar inverse square law. But if extra dimensions exist, gravity could become stronger at distances smaller than the size of those dimensions. Physicists have performed tabletop experiments using torsion balances to test gravity at distances as small as a few tens of microns, the width of a human hair. So far, no deviation has been found. That means if extra dimensions are real, they must be curled up smaller than about 1/10 of a millimeter. The brane world scenario paints a radical picture. Our universe is a 3-dimensional membrane or brane embedded in a higher dimensional bulk. All the particles and forces we know except gravity are stuck to our brane. Gravity, however, can wander into the bulk. That means gravity is diluted on our brane, explaining its weakness. Some versions of brane cosmology predict that other branes could exist nearby, maybe even parallel universes separated by a thin gap in the extra dimension. Those branes could collide, causing ripples that we might detect as gravitational waves or as subtle patterns in the cosmic microwave background. The idea of extra dimensions also connects to dark matter. Some theories propose that dark matter particles are actually gravitons, the carriers of gravity that have escaped into the bulk and are now trapped in a thin layer around our brane. Or they could be particles living on a different nearby brane, interacting with us only through gravity. Each of these possibilities leaves a unique fingerprint in the way galaxies rotate and in the way matter clusters. For now, extra dimensions remain a tantalizing possibility, a hidden layer of reality that our current experiments have not yet reached. But the search continues, both at the smallest scales with colliders and torsion balances, and at the largest scales with cosmological surveys. If we ever detect a mini black hole or a tiny deviation in gravity, it will confirm that our 3-dimensional world is just a slice of a much larger, stranger cosmos. And that raises an even more profound question. If our universe is a brane, could there be other branes drifting through the bulk, maybe even touching ours? Our universe may be a 3-dimensional island drifting in a higher dimensional sea. That island is called a brane, short for membrane, and the surrounding ocean is the bulk. All the particles and forces we know, except gravity, are stuck to our brane. They cannot leave its surface no matter how much energy we use, but gravity is different. Gravity can leak into the bulk like a faint whisper escaping through a crack in a sealed room. That leakage explains one of the deepest puzzles in physics, the hierarchy problem. Why is gravity so much weaker than the other fundamental forces? The electromagnetic force between two protons is about 10,000 billion times stronger than their gravitational attraction. That enormous gap has bothered physicists for decades. In the brane world, the answer becomes clear. Gravity appears weak to us because most of its strength spreads out into the extra dimensions of the bulk. What we feel on our brain is only a tiny fraction of the full gravitational force. It is like standing next to a waterfall and only feeling a few drops of spray because the rest of the water pours into a hidden cavern underground. If gravity really does leak into the bulk, it should leave observable traces. One such trace would be deviations in the law of gravity at very small distances. On our brain, gravity follows the familiar inverse square law, but if an extra dimension is large enough, gravity could become stronger at scales shorter than the size of that dimension. Tabletop experiments using delicate torsion balances have searched for such deviations down to about 10 millionths of a meter, and so far they have seen nothing. That means if the extra dimension exists, it must be curled up smaller than that, but another signature could appear in gravitational waves. When two massive objects merge, they send ripples across spacetime. If those ripples pass through the bulk, they could carry a subtle extra component that does not obey the normal inverse square damping. Future detectors like LISA or next-generation ground-based observatories might catch an anomaly in the waves, a tiny extra pulse or a change in shape that standard general relativity cannot explain. Some theories even suggest that colliding branes, two nearby branes touching in the bulk, could generate their own gravitational wave bursts, a kind of cosmic echo from a hidden dimension. For now, the brane world remains a speculative but compelling picture. It unifies the forces, solves the hierarchy problem, and opens the door to parallel universes just a sliver of extra space away. And it points toward an even stranger idea, that all the information in our three-dimensional world might be encoded on a two-dimensional surface. That is the holographic principle, a clue that the true nature of reality may be far more subtle than anything we have touched so far. The most extraordinary implication of the brane world is that our entire universe might be a projection. This idea is called the holographic principle, and it suggests that everything we experience, every star, every galaxy, every thought, could be an illusion cast from a two-dimensional surface at the edge of reality. The concept was born from black hole thermodynamics. In the 1970s, physicists discovered that black holes have a temperature and an entropy, a measure of disorder. The entropy of a black hole is proportional not to its volume but to the area of its event horizon. That was strange. In normal physics, entropy scales with volume. But for a black hole, all the information about everything that fell in seems to be stored on the surface. This led Gerard T. Hooft and Leonard Susskind to propose the holographic principle. The three-dimensional world inside a black hole could be fully described by information encoded on its two-dimensional boundary. They then asked if the same could be true for the entire universe. If it holds for black holes, why not for the cosmos itself? The idea gained a rigorous mathematical foundation through the ADS/CFT correspondence, a discovery made by Juan Maldaisner in the late 1990s. He showed that a certain type of universe called anti-de Sitter space, which has negative curvature, is mathematically equivalent to a quantum field theory living on the boundary of that space. In simple terms, a universe with gravity in its interior is perfectly mapped onto a surface without gravity. The two descriptions produce identical predictions. One is three-dimensional with gravity, the other is two-dimensional without gravity. They are dual, two sides of the same coin. If this duality applies to our universe, then our apparently three-dimensional reality, with all its mass and energy and motion, is simply a holographic projection of information stored on a distant, fundamental surface. That surface would be like a cosmic hard drive, containing every bit of data needed to render the full volume of space and time. the hidden structure of the universe would then be a two-dimensional grid of quantum bits, not a three-dimensional fabric at all. What does this mean for the way we see the cosmos? It suggests that space itself is not fundamental. It is an emergent property, like the image on a computer screen. The pixels on the screen are the true reality, and the picture they form is a convenient illusion. In the same way, the three dimensions we move through might be a kind of user interface, a simplified display of a deeper, simpler code. This has profound implications for the nature of black holes. If the holographic principle is correct, then when something falls into a black hole, its information is not lost. It is smeared across the event horizon, preserved on that two-dimensional surface. This resolves the famous black hole information paradox, a long-standing conflict between quantum mechanics and general relativity. The information is never destroyed, only encoded in a different form, and if black holes are holograms, then perhaps the entire universe is too. The idea is still being tested. Researchers have used the ADS/CFT correspondence to model phenomena as diverse as quark-gluon plasma and superconductivity, but applying it to our expanding, positively curved universe is more difficult. Our cosmos is not anti-de Sitter space, yet many physicists believe the holographic principle is a universal truth. It may be the first glimpse of a theory of quantum gravity, a framework that unifies the large and the small. If so, then the hidden structure of reality is not a web of dark matter filaments or extra dimensions, but a vast two-dimensional surface of information, projecting the illusion of a three-dimensional world. That surface holds the final answer to what lies inside a black hole, and maybe even what lies beyond the edge of the observable universe. But to understand that, we must look deeper into the interior of a black hole itself, where the laws of physics as we know them break down entirely. At the core of every black hole lies a place where physics stops making sense. According to standard general relativity, the heart of a black hole is a singularity, a single point where matter is crushed to infinite density and spacetime curvature becomes infinite. At that point, the equations that describe gravity break down completely. They simply stop working, giving infinities that have no physical meaning. This is not just a mathematical glitch. It is a clear sign that general relativity, which works so well everywhere else, cannot describe what happens inside a black hole. Something else must take over, something rooted in the quantum world. For decades, physicists have been searching for a theory that can smooth out that singularity, replacing the infinite point with a finite, real structure. One of the most promising ideas is the fuzzball. In string theory, black holes are not empty voids with a point at the center. They are dense, tangled balls of strings, the fundamental building blocks of matter. Each string is a tiny, vibrating loop, and when enough of them accumulate, they form a fuzzy sphere that looks like a black hole from the outside but has no singularity inside. The fuzzball's surface is not a smooth event horizon but a chaotic quantum surface where space itself is made of strings. If you tried to fall into a fuzzball, you would not reach a point of infinite density. Instead, you would hit the fuzzy surface and become part of the tangled ball. Information would not be lost, it would be encoded in the arrangement of strings. This resolves the black hole information paradox in a natural way. Another theory proposes a Planck star. This idea combines loop quantum gravity with black hole physics. In loop quantum gravity, space itself is quantized, made of tiny discrete grains. When matter collapses to form a black hole, it does not crush down to a point. Instead, it reaches a maximum density determined by the size of those grains. At that point, the collapse stops and rebounds, creating a star made of Planck-scale matter. From the outside, this object still looks like a black hole, but inside, the singularity is replaced by a small, dense ball of quantum geometry. The rebound could even cause the black hole to eventually explode, releasing its contents in a burst of radiation. Both the fuzzball and the Planck star avoid the infinite singularity. They replace it with a finite, physical object that obeys the rules of quantum gravity. But there is an even stranger possibility. Some equations suggest that inside a black hole, space and time swap roles. Normally, you can move freely in space but are forced forward in time. Inside a black hole, the geometry flips. The singularity becomes a moment in time, not a place in space. You cannot avoid it any more than you can avoid tomorrow. But in that warped interior, there might be a tunnel, a passage through the singularity to somewhere else. That tunnel is a wormhole. Some solutions to Einstein's equations allow black holes to connect to white holes, hypothetical objects that spit matter out instead of swallowing it. The throat between them is a wormhole. If such a wormhole exists, falling into a black hole might not end in destruction. It could lead to another region of the same universe, or even to a different universe entirely. The tunnel would be unstable, pinching off too fast for anything to pass through unless held open by some exotic form of matter with negative energy. That exotic matter is not known to exist in bulk, but quantum fields can produce fleeting amounts of it. The question is whether enough could be gathered to keep a wormhole open. The idea of wormholes has captured the public imagination, but it rests on the question of what really lies inside a black hole. Is it a singularity, a fuzzball, a Planck star, or a bridge to somewhere else? Each answer rewrites the hidden structure of reality in a different way, and each answer points toward the next frontier. The possibility that space itself is riddled with shortcuts, tunnels that could connect distant points or different eras. The hunt for that hidden network is just beginning. Wormholes might be the most direct shortcut through the fabric of spacetime. Imagine a tunnel that connects two separate points in the universe, bending space so dramatically that the distance between them becomes almost nothing. A journey that would take thousands of light years could, in theory, be crossed in an instant. This idea comes directly from Einstein's equations of general relativity. In 1935, Einstein and his colleague Nathan Rosen discovered a solution that described a bridge linking two distant regions of spacetime. They called it an Einstein-Rosen bridge. At first, it seemed like a mathematical curiosity, a wrinkle in the geometry that had no physical meaning. But later physicists realized that such a bridge could form inside a black hole. The singularity at the center of a black hole might not be a dead end. Instead, it could be the throat of a wormhole, a passage that leads to another black hole elsewhere in the cosmos, or even to a completely different universe. The tunnel itself is not stable. In standard general relativity, the wormhole pinches off so quickly that nothing, not even light, can travel through it. The throat collapses before anything can cross. That is where exotic matter comes in. Exotic matter is a theoretical material that has negative energy density. Unlike ordinary matter, which pulls things together with gravity, exotic matter pushes them apart. If enough exotic matter lines the throat of a wormhole, it can counteract the immense gravitational squeeze and keep the tunnel open. The problem is that exotic matter does not exist naturally in large, stable quantities. Quantum mechanics allows tiny amounts of negative energy to appear briefly in empty space, a phenomenon called vacuum fluctuations. But those fleeting bursts are far too small to hold a wormhole open for anything larger than a subatomic particle. Some theories suggest that if we could somehow gather or create a macroscopic amount of exotic matter, we could stabilize a traversable wormhole. That would be an engineering challenge far beyond anything we can imagine, but the physics does not forbid it. Even without a stable wormhole, we might still detect their presence indirectly. If a wormhole existed somewhere in the universe, its immense gravity would bend light passing nearby, just like a black hole does. This is called gravitational lensing. But a wormhole would produce a distinctive pattern of multiple images, different from what a black hole or a galaxy cluster creates. Astronomers scanning the sky for gravitational lensing events have not yet found a clear candidate, but the search continues with ever more sensitive telescopes. A wormhole could also reveal itself through its effect on the orbits of stars around the center of a galaxy. If a supermassive black hole at a galactic core is actually a wormhole, the stars circling it would move in a slightly different pattern than expected. Future observations of the Milky Way's center using instruments like the Event Horizon Telescope could pick up those subtle deviations. Wormholes also play a key role in quantum gravity theories. In string theory, the same mathematical structures that describe particle interactions can also describe tiny wormholes that connect different regions of space. These are called Euclidean wormholes, and they appear in calculations of quantum gravity as fleeting connections between distant points. They might be responsible for the fine-tuning of the universe's fundamental constants, allowing different regions to share information across vast distances. The idea of a traversable wormhole pushes the boundaries of what we consider possible. It forces us to ask whether the universe is a network of hidden shortcuts, a kind of cosmic subway system linking distant stations. The next theory takes that idea even further, suggesting that such shortcuts might not only exist but could be stable enough for something to actually pass through. Recent advances in theoretical physics suggest a way around that exotic matter problem. Modified models of general relativity show that wormholes might be held open by more familiar things, quantum fields or the geometry of extra dimensions. Instead of needing negative energy, these models rely on the subtle behavior of quantum particles in curved spacetime. For example, a particular configuration of the quantum vacuum, the sea of fleeting particles that fills empty space, can generate a repulsive force strong enough to prevent the throat from collapsing. Similarly, in theories with extra dimensions, the gravitational field can leak into the bulk in a way that stabilizes the tunnel. This means traversable wormholes might not require exotic matter at all. They could be natural consequences of physics we already suspect exists. Where might such wormholes hide? One possibility is at the centers of galaxies. The supermassive objects we call black holes might actually be the mouths of wormholes, their event horizons masking a passage to another region of spacetime. If that were true, the stars orbiting the galactic center would move in patterns subtly different from those predicted by black hole models. Future observations with instruments like the Event Horizon Telescope could reveal those differences. Another possibility is that microscopic wormholes are woven into the quantum foam itself. Just as virtual particles pop in and out of existence, so too could tiny tunnels connecting distant points. These would be far too small for anything to pass through, but they could still leave an imprint on the fabric of spacetime, subtly affecting how light travels over cosmic distances. The speculative nature of these ideas cannot be overstated. They push into territory where even the math becomes uncertain, and they bring up a strange consequence. If wormholes can be traversed, they might also allow travel backward in time. A wormhole with one mouth moving at relativistic speeds or placed near a strong gravitational field could create a closed loop, an effect known as a closed time-like curve. This raises the grandfather paradox, where changing the past could undo the journey itself. Quantum mechanics offers a possible resolution. Some interpretations suggest that the universe would form self-consistent loops, forbidding any paradox. Others point to the many worlds interpretation, where each change splits off a new timeline. This idea of branching universes leads directly to the next layer of hidden structure, the multiverse. If wormholes connect different regions of spacetime, they might also connect different universes, each with its own laws and history. The barrier between worlds could be thinner than we ever imagined. That barrier might be no thicker than the edge of our cosmic horizon. Beyond the farthest galaxies and the faintest afterglow of the Big Bang lies a boundary we can never cross, not because it is physically impassable, but because the light from beyond it has not had time to reach us. Yet according to the theory of eternal inflation, that horizon does not mark the end of the universe. It marks the beginning of countless others. This idea emerged from the study of cosmic inflation, the brief period of exponential expansion that occurred fractions of a second after the Big Bang. In the standard picture, inflation ended in our region, allowing matter and energy to settle into the universe we see today. But the theory suggests that inflation does not stop everywhere. In some regions, space continues to inflate eternally, while in others it stops, forming bubbles of ordinary spacetime. Each bubble is a separate universe, a domain with its own Big Bang, its own laws of physics, and its own cosmic history. We live inside one such bubble, and beyond our horizon, an infinite number of other bubbles may exist, each born from a different quantum fluctuation in the inflating background. The simplest type of multiverse is known as level I. In this picture, the laws of physics are the same everywhere, but the initial conditions differ from one Hubble volume to another. Our observable universe is a sphere about 93 billion light-years across. Beyond that, space stretches on forever, but we can never see it because light from those regions has not reached us. Level I says that if you traveled far enough, you would eventually find a region identical to ours, due to the finite number of ways particles can arrange themselves in a finite volume. The number of possible configurations is enormous but limited. So in an infinite universe, every pattern repeats. Somewhere out there, another Earth exists with another you, living through the same moment. That is a consequence of infinity and the laws of probability, not of exotic physics. Level Roman 2 goes further. Here the different bubble universes from eternal inflation can have different vacuum states, meaning the fundamental constants and even the elementary particles might be completely different in each bubble. The vacuum state is the lowest energy configuration of empty space. In our universe, that state allows electrons, protons, and the forces we know. In another bubble, the vacuum could have a different value, making gravity stronger or the speed of light slower, or eliminating some forces entirely. These variations arise because the inflattened field, the energy field that drove inflation, can settle into different valleys in its energy landscape. Each valley corresponds to a different set of physical laws. This is not just a hypothetical possibility. The idea is grounded in string theory, which predicts a vast landscape of possible vacuum states, perhaps 10 to the 500 or more. Each bubble universe picks one of these states randomly. Most of these universes are sterile, unable to form galaxies, stars, or life. But in a multiverse of infinite size, even a tiny fraction of hospitable bubbles yields an enormous number of living worlds. All these other universes are hidden from us. They lie beyond the cosmic horizon, separated by vast stretches of still inflating space. We can never see them directly because light from a bubble universe cannot travel through the inflating background between bubbles. The expansion is too rapid. The only possible way to detect evidence of another bubble would be if ours collided with one in the distant past. Such a collision would leave a scar on the cosmic microwave background, a circular pattern of slightly hotter or colder temperature. Astronomers have searched the Planck satellite maps for such a signature, but no convincing candidate has been found. That does not rule out the multiverse. It only tells us that no bubble has hit ours in the last 13.8 billion years. The multiverse is a radical idea, one that challenges our notions of uniqueness and purpose. It removes the need for fine-tuning because every possible combination of constants exists somewhere. It also raises a deep question. If there are infinitely many universes, what does it mean for a theory to be correct? A theory that predicts everything predicts nothing. Physicists grapple with this problem, trying to find a way to make testable predictions despite the infinite possibilities. Some look for statistical patterns, like the typical size of a bubble or the distribution of certain parameters. Others search for indirect clues in the way our own universe is structured. The multiverse remains speculative, but it is a natural consequence of inflation and string theory. It pushes the hidden structure of reality beyond the fabric of spacetime itself, into a realm where the very concept of universe becomes just one bubble in an endless sea. And from that sea, even stranger possibilities emerge, like universes that exist side by side in extra dimensions. The quantum world offers a vision of reality that branches with every decision. This is the core of the many worlds interpretation of quantum mechanics, often called level Roman 3 of the multiverse. In the standard view, a particle exists in multiple states at once, a superposition, until we measure it and the wave function collapses into a single outcome. But the many worlds interpretation says there is no collapse. Instead, every possible outcome actually happens, each in its own separate branch of reality. When you measure a particle, the universe splits. One copy of you sees the particle spin up, another sees it spin down. Both branches continue to evolve independently, each as real as the other. This means that at every moment, an immense number of new realities are being created, all hidden from one another by the very laws of quantum mechanics. You cannot feel these branches, but the mathematics suggests they are there, forming a vast, invisible tree of parallel histories. Every choice you make, every quantum event, every random fluctuation, all of them multiply the number of worlds beyond counting. This is not science fiction. It is a direct interpretation of the equations that describe the subatomic world. Some physicists accept it as the most straightforward reading of quantum theory. Others reject it because it introduces so many unobservable universes. But if it is true, then the hidden structure of reality includes an infinite number of copies of you, living through every possible variation of your life. And that is only one layer of the multiverse. Level Roman 4 pushes the idea even further. This is the mathematical universe hypothesis proposed by physicist Max Tegmark. It states that any mathematical structure that is self-consistent exists as a physical universe. In other words, the set of all possible mathematical equations and logical systems is not just an abstract realm of ideas. Each internally consistent set of rules gives rise to a real universe with its own space, time, matter, and laws. Our universe is just one among an infinite ensemble of mathematical structures. Some of those structures might be incredibly simple, like a single point with no dimensions. Others might have 11 dimensions or fractional dimensions or no time at all. Most would be barren, too simple to support any form of complexity, but a few, like ours, would allow the emergence of galaxies, stars, and life. The mathematical universe hypothesis dissolves the fine-tuning problem completely. Our universe appears finely tuned for life because we could only exist in a universe that allows life. But in a multiverse where every possible set of laws exists, it is no surprise that we find ourselves in one that works. The fine-tuning is simply a selection effect, a matter of perspective. This is the most radical version of the multiverse. It says that reality is not just the physical world we observe, but the entire Platonic realm of mathematics given existence. Every possible universe, every possible history, every possible physical law, all exist side by side in a vast, abstract structure. And this leads to a startling question. If all mathematical structures are real, then what about universes that are not defined by laws of physics but by computational rules? A computer simulation is a mathematical structure. If it is internally consistent, it too would exist as a real universe. That idea is the simulation hypothesis, and it takes the hidden structure of reality into a realm where nothing is as it seems. That code could be written in the fabric of spacetime itself. The simulation hypothesis proposes that everything we see, feel, and measure is not a physical reality but a computational output, a vast program running on a system far beyond our comprehension. This idea has moved from the edges of science fiction to a serious topic in philosophy and physics because it offers a clean explanation for some of the deepest puzzles about our universe. The first puzzle is the fine-tuning problem. The constants of nature, the strength of gravity, the mass of an electron, the expansion rate of the cosmos, all seem set to incredibly precise values. If any of them were off by even a tiny fraction, stars would not form, galaxies would not coalesce, and life would be impossible. In a simulated universe, that fine-tuning is not an accident. It is the result of a programmer choosing the settings that allow a complex, interesting world to emerge. Just as a game designer tweaks the rules of a virtual world to make it playable, the architect of our simulation could have dialed in these numbers deliberately. The second argument comes from computational power. As our own computer simulations grow more complex, we can model galaxies, weather, and even simple forms of life. A sufficiently advanced civilization would eventually have the ability to simulate entire universes. If that is possible, then it becomes statistically likely that the number of simulated universes vastly outnumbers the one base reality. In that case, we are probably inside a simulation right now, simply because there are so many more simulated minds than real ones. The hidden structures of such a simulation would be very different from the fabric of actual spacetime. Instead of a smooth continuum, the simulated universe would have a fundamental resolution, a kind of pixelation at the smallest scale. This is the computational equivalent of the pixels on a screen. In our universe, that pixel would be the Planck length, the smallest possible distance. But in a simulation, there might be a slightly larger grid, a limit on how fine the space and time can be divided. That limit would leave subtle fingerprints. For example, the energy of cosmic rays, the most energetic particles that zoom through space, should follow a smooth distribution according to standard physics. But if spacetime is pixelated, there might be a cutoff, a maximum energy beyond which no particle can exist. Some experiments have reported an unexpected drop in very high-energy cosmic rays, a hint that something is imposing an upper bound. That could be the grid size of the simulation. Another possible test involves the cosmic microwave background, the faint glow left over from the Big Bang. In a simulated universe, this background might show tiny repeating patterns, like the repeating tiles of a wallpaper. If the simulation uses a limited amount of memory to store the entire universe, it might reuse the same pattern across different parts of the sky. Astronomers have searched the maps from the Planck satellite for such repeating patterns, and while no clear evidence has been found, the search continues with ever more sensitive instruments. What does it mean if we are living in a simulation? It does not change the reality of our experiences. The pain, the joy, the beauty of a sunset are still real to us. But it does mean that the universe we study is a construct, a code written by some intelligence. That code could be running on a machine that exists in a higher layer of reality, a reality we can never directly access. The laws of physics we discover are then the rules of the program, not the fundamental truths of existence. The simulation hypothesis leads naturally to an even stranger idea. If the universe is a program, then perhaps the fundamental unit of that program is not a particle or a field, but a node in a vast network, a network that learns and adapts. That is the universe as a neural network, where the hidden structure is not a grid of pixels but a web of connections, constantly updating itself. Some physicists now wonder if the universe is not just like a computer, but more like a brain. Not a biological brain with neurons and synapses, but a vast network of connections where information flows and patterns emerge. In this view, the fundamental laws of physics are not set in stone. They are learned, or at least they arise from the interactions of countless simple components, much like a neural network in machine learning that discovers rules from data. This theory, sometimes called the universe as a neural network, suggests that space, time, matter, and energy are all emergent phenomena. They are not the most basic building blocks. Instead, the deepest layer of reality is a web of connections, a kind of graph where every point is linked to others in a specific way. From those links, higher-level structures like particles, fields, and even gravity can appear naturally without needing a separate set of equations. Think of how a large artificial neural network, after training on thousands of examples, can recognize faces or translate languages. It never explicitly learns the rules of grammar or geometry. Those rules emerge from the weights on its connections. In the same way, the laws of physics could emerge from the hidden architecture of the cosmos. That architecture might be a single, self-updating network that constantly refines its own behavior. This idea offers a way to unify quantum mechanics and general relativity, two theories that have resisted unification for a century. In the network model, both quantum behavior and curved spacetime are not fundamental. They are different aspects of the same underlying process, like how the same neural net can give rise to both a memory and a prediction depending on the input. Spacetime itself might be a form of neural activity, a dynamic pattern that carries information and evolves over time. If that is true, then the hidden structure of the universe is not made of particles or strings. It is made of pure relationship, a web of cause and effect that learns as it grows. This leads to a fascinating possibility. The network might be governed by a simple rule, a rule that repeats across the whole system. And that rule could be as basic as a cellular automaton, where space is divided into cells and each cell updates its state based on its neighbors. From such minimal rules, enormous complexity can arise. The universe as a neural network points toward an even simpler foundation, one where the fabric of reality is a vast, self-organizing grid. That self-organizing grid may be the simplest rule of all. The idea that the entire universe runs on a set of basic instructions, like a program that updates itself step by step, is called a cellular automaton. The classic example is Conway's game of life, a simulation on a two-dimensional grid of cells. Each cell is either alive or dead, and its next state depends only on the number of living neighbors around it. From those 3 or 4 lines of logic, staggeringly complex patterns emerge. Gliders that move across the screen, oscillators that pulse, even structures that can mimic a computer. No central planner, no hidden forces, just simple rules repeated over and over. Some physicists have wondered if our universe works the same way. In this picture, space is not a smooth continuum but a lattice of discrete points like the pixels on a screen. Time, too, is not a flowing river but a series of ticks, each instant following the last according to a fixed rule. What we experience as continuous motion, smooth curves, and flowing fields would then be an illusion, a kind of movie made from many still frames shown in rapid succession. The laws of physics we measure, gravity, electromagnetism, quantum mechanics, would be emergent phenomena, higher-level patterns that arise from the underlying grid. This idea is not as far-fetched as it sounds. Quantum mechanics already hints at a discrete world. Energy comes in packets called quanta. Particles exist at specific points until they move. Spin and other properties take on only certain values. All of this suggests that nature has a built-in granularity. A cellular automaton would explain why. The rules of the grid would naturally produce quantum behavior as a statistical effect, while the deeper reality remains deterministic. One candidate for such a rule is the theory of causal sets, where spacetime itself is built from a set of point events linked by cause and effect. Another is Wolfram physics, a project that attempts to find a single rule that generates all of physics. No definitive evidence has been found yet, but the search has revealed something striking. The fine-tuning problem that plagues standard cosmology, the precise values of constants, the delicate balance of forces, would no longer be a mystery. In a cellular automaton universe, the rules are fixed from the start. The constants are not tuned by chance or by a designer. They are inevitable consequences of the chosen rule, just as the speed of light in a cellular automaton emerges from the grid spacing and update rate. If the rule is the only thing that exists, then the constants are not fine-tuned at all. They are necessary. This shifts the question from why the universe is so special to why this particular rule exists. And that is a question that may lead toward an even deeper layer, where the rule itself is not chosen but is the only possible consistent one. The constants of nature are not arbitrary. They are set with astonishing precision, as if each one were chosen from an infinite set of possible values. The strength of gravity, for example, is so finely balanced that if it were ever so slightly stronger, the universe would have collapsed back on itself moments after the Big Bang. If it were weaker, no stars would have formed, and the cosmos would have remained a dark, diffuse fog. The cosmological constant, the energy that drives the accelerating expansion of space, is even more extreme. Theoretical calculations suggest it should be about 10 to the 120 times larger than what we observe. That discrepancy is the worst prediction in all of physics. Yet the actual value is just right for galaxies to form and life to emerge. This cascade of coincidences is called the fine-tuning problem. It has led physicists to consider two very different kinds of hidden structures. One possibility is that our universe is just one among countless others, each with different constants, and we happen to live in one that allows life because we could not exist in any other. This is the anthropic principle, a form of reasoning based on selection bias. It does not explain why the constants are what they are, but it explains why we observe them to be that way. In a multiverse where every possible combination exists, the fine-tuning is no longer surprising, it is inevitable. The alternative is that the constants are set by a deeper principle, perhaps a single mathematical law that forces them to take exactly these values. That would mean the hidden structure is not a multiverse but a unified equation, one that governs everything from the spin of an electron to the curvature of spacetime. Some researchers look for such a principle in the symmetries that underlie the laws of nature, because symmetry often dictates what is allowed and what is forbidden. The fine-tuning of the cosmological constant, for instance, might be a clue that we are missing a symmetry that exactly cancels out the enormous vacuum energy predicted by quantum field theory. That missing symmetry would be a hidden structure as profound as any we have considered, a kind of cosmic balance that keeps the universe stable enough for life. The question of why the universe is so precisely tuned is not just a puzzle for physics, it is a doorway to the most fundamental layer of reality, and that layer may be governed by symmetry, the silent architect of everything we see. Symmetry is not just a property of shapes, it may be the hidden force that keeps the universe from tearing itself apart. The hierarchy problem, that enormous gap between the weak force and gravity, could be solved if every known particle had a heavier twin. That is the core of supersymmetry, often shortened to SDSS, a theory that pairs each fermion, the particles that make up matter, with a boson, a particle that carries force, and vice versa. For every electron there would be a selectron, for every quark a squark, for every photon a photino. These superpartners would be far more massive than their ordinary counterparts, explaining why we have not seen them yet. Their existence would cancel out the quantum fluctuations that would otherwise drive the mass of the Higgs boson to enormous values, the very fine tuning that has puzzled physicists. And the lightest superpartner would be stable, electrically neutral, and interact only weakly with normal matter, making it a perfect candidate for dark matter. The universe could be filled with these particles, invisible but heavy, shaping galaxy formation without ever emitting light. But despite decades of searching at the Large Hadron Collider, no superpartner has appeared. The collider has pushed its energy to 13 trillion electron volts and still nothing. That silence has forced theorists to consider that SDSS might be hiding in places we have not looked. Perhaps the superpartners are too heavy for the current collider to produce, or they could be decaying in ways that make them hard to detect. Some versions of the theory place them in extra dimensions where their mass is spread out across a hidden geometry, weakening their signature. Others suggest that SDSS is broken at very high energies, far above the reach of our most powerful machines. If that is true, then the dark matter from supersymmetry would be a relic from an era so hot that even the superpartners existed in equilibrium, slowly freezing out as the universe cooled. The question of why SDSS remains hidden is one of the deepest puzzles in modern physics. It points toward another fine-tuning problem, one involving the strong nuclear force. That force does not violate a certain symmetry called charge parity, but it could, and the fact that it almost perfectly does not is known as the strong CP problem. The solution to that problem may involve a new particle, the axion, and that is exactly the next hidden structure we need to explore. The strong CP problem is named for its connection to charge and parity, two fundamental properties of particles. Charge flips a particle to its antiparticle, and parity flips left and right. Together, they form a symmetry that the strong nuclear force, the force that binds quarks into protons and neutrons, almost perfectly obeys. It almost perfectly obeys, but it could easily break, and the fact that it does not break to any measurable degree is a mystery. Physicists have calculated that the strong force could violate charge parity by a tiny amount, but every experiment sees no violation at all. That fine-tuning, where a number that could be as large as 1 is instead less than 1/10,000,000th, screams for an explanation. The most elegant solution came from Roberto Pecci and Helen Quinn in 1977. They proposed a new symmetry, one that would dynamically cancel out any charge parity violation. And that symmetry implied the existence of a new particle, which Frank Wilczek named the axion, after a brand of laundry detergent because it cleaned up a problem. The axion would be incredibly light, perhaps a billionth of the mass of an electron, and it would interact so weakly with ordinary matter that it barely touches anything. Yet it would permeate the universe as a vast, invisible field, like a faint breeze blowing through every point in space. That field is the hidden structure that solves the puzzle. In the early universe, this axion field would have been jostled by the heat of the Big Bang. As the universe expanded and cooled, the field began to oscillate like a pendulum swinging. Those oscillations would have produced a sea of axion particles, and because they are so stable and so light, they would never decay. They would simply linger, slowly clustering under gravity. And here is the remarkable part. If axions exist and have the right mass, they would naturally account for all the dark matter in the cosmos. They would be cold, meaning they move slowly, and they would clump together into enormous, invisible clouds that stretch across galaxies. These clouds would not be uniform. Theorists believe that axions can condense into a state of matter called a Bose-Einstein condensate. In that state, vast numbers of axions lose their individual identities and behave as a single, coherent wave. Imagine a ghostly ocean stretching for light years where every particle moves in perfect unison. This condensate would have strange properties. It could form vortices like tiny whirlpools in the axion field, or it could ripple with waves that carry energy across cosmic distances. These condensates might even form axion stars, dense clumps where the field becomes so strong that it interacts with itself. How could we ever detect something so elusive? The axion interacts with electromagnetism in a special way. In the presence of a strong magnetic field, an axion can convert into a photon, a particle of light. This conversion is the key to every detection experiment. One type of device is called a haloscope. It uses a resonant cavity, a hollow metal box placed inside a powerful magnet. If axions from the dark matter halo around Earth pass through that cavity, some of them should turn into photons, creating a tiny signal at a specific frequency. By tuning the cavity over a range of frequencies, researchers like those on the Axion Dark Matter Experiment, or ADMX, have been scanning for decades. So far, they have ruled out a range of masses, but the search continues, slowly creeping toward the most theoretically favored values. Another type of device is a helioscope. Instead of looking for dark matter actions, it looks for actions produced inside the Sun. The Sun's core is hot and dense enough to create actions through nuclear reactions. These solar actions stream out in all directions. A helioscope, like the CERN Action Solar Telescope or the planned IOXO, aims a powerful magnet at the Sun. When solar actions enter the magnet, they can convert into X-ray photons, which then get detected. The challenge is that the expected signal is extremely faint, far weaker than the background noise. But with careful shielding and long observation times, the signal could emerge. The discovery of the action would solve two problems at once, the strong CP problem and the dark matter mystery. It would reveal a hidden field that fills the entire universe, a field that was born in the first moments of creation and has been oscillating ever since. And it would point toward even stranger particles like the sterile neutrino, which may hold the key to the missing mass in ways that actions cannot explain. The hunt continues, and every quiet, patient experiment brings us closer to hearing the faint whisper of a particle that has been waiting to be found for 13.8 billion years. There is another ghostly particle that might be even harder to find. Ordinary neutrinos are already famously elusive, streaming through our planet by the trillions every second with barely a trace. But the sterile neutrino is a different kind of phantom entirely. Unlike the familiar trio of neutrinos that interact through the weak nuclear force, the sterile neutrino would only respond to gravity. It does not feel the weak force, it does not feel the electromagnetic force, and it does not feel the strong force. It is truly a solitary wanderer, touching the rest of the universe only through the pull of its mass. Why would such a particle exist in the first place? The answer comes from a puzzle in particle physics known as the seesaw mechanism. Ordinary neutrinos are extraordinarily light, millions of times lighter than an electron. That tiny mass seems unnatural compared to other particles. The seesaw mechanism explains it by pairing each ordinary neutrino with a much heavier sterile partner. The heavier the sterile neutrino, the lighter its ordinary counterpart becomes, like a seesaw where one side goes down as the other rises. In this picture, the sterile neutrino could have a mass anywhere from a few thousand electron volts up to billions of times the mass of a proton. And that mass range makes them a compelling candidate for dark matter. If sterile neutrinos have a mass in the kiloelectron volt range, around a few thousand times the mass of an electron, they would behave like warm dark matter. Not as fast as hot dark matter like ordinary neutrinos, which would wash out galaxy formation, and not as slow as cold dark matter, which clumps too efficiently. Warm dark matter from sterile neutrinos would produce a universe that looks very much like our own, with the right number of dwarf galaxies and the correct structure of the cosmic web. In fact, simulations show that a sterile neutrino with a mass of about 7 kiloelectron volts can match many of the observed properties of the universe. How would such particles be created in the early universe? One method involves mixing with ordinary neutrinos. In the intense heat of the Big Bang, sterile neutrinos could be produced through oscillations, a quantum process where an ordinary neutrino transforms into a sterile one. The rate of this production depends on the tiny mixing angle between the two types. If that mixing is just right, the sterile neutrinos would be created in exactly the abundance needed to account for all the dark matter. But they would not be produced too early, because if they were, they would be too energetic and would stream too fast, suppressing the formation of small galaxies. That is why sterile neutrinos are sometimes called warm dark matter. Their temperature and motion place them in a sweet spot between the cold and hot extremes. Another production mechanism involves a different process called the She-Fuller mechanism. In this scenario, sterile neutrinos are created by a resonance that occurs when the universe is about a second old. This produces a narrower spread of momenta, making the dark matter even colder and more consistent with observations. The details are intricate, but the key point is that sterile neutrinos can be made in the early universe without needing any new forces or particles beyond the ones we already know. If sterile neutrinos are real and make up dark matter, they would be spread throughout the galaxy in a faint, tenuous halo. They would be almost impossible to detect directly because they barely interact with anything. But there is a possible indirect signal. If the sterile neutrino has a certain mass and a tiny mixing with ordinary neutrinos, it can undergo a slow decay. A sterile neutrino would occasionally transform into an ordinary neutrino and a photon of X-ray light. This decay is incredibly rare, with a lifetime longer than the current age of the universe. But because there are so many sterile neutrinos in the galaxy, the cumulative glow from all those rare decays could be just barely visible. Astronomers have searched for a faint, unexplained X-ray line coming from dark matter-rich regions like the centers of galaxies or galaxy clusters. In 2014, a team analyzing X-ray data from the Chandra and XMM Newton telescopes reported a weak signal at an energy of about 3.5 kiloelectron-volts. This line, seen in the spectra of several galaxy clusters and the Andromeda galaxy, matched the expected signature of a decaying sterile neutrino with a mass of 7 kiloelectron-volts. The result generated enormous excitement, but subsequent studies with other instruments and deeper data have been inconclusive. Some observations see the line, others do not. The signal may be real, or it may be an artifact of the calibration or instrumental background. The debate continues. Even if the 3.5 kiloelectron-volt line ultimately disappears, sterile neutrinos are far from ruled out. Their mass could be higher or lower, placing their decay signal in a different energy range. Future missions like the Athena X-ray Observatory or the E-Rosetta survey will scan the sky with greater sensitivity and resolution, offering a clearer view of the X-ray sky. The hunt for sterile neutrinos is also being pursued in laboratory experiments. Because they mix with ordinary neutrinos, they could show up in experiments designed to detect neutrino oscillations. The mini-BUNI and micro-BUNI experiments at Fermilab have seen anomalies that might hint at a sterile neutrino, but the evidence remains controversial. The sterile neutrino sits at a curious crossroads. It is a natural extension of our best theory of particle physics, the Standard Model, and it solves both the mystery of neutrino masses and the identity of dark matter. And it connects directly to the very early universe, serving as a messenger from a time when the cosmos was less than a second old. If we ever detect the faint X-ray glow of its decay, or find its signature in a neutrino oscillation experiment, we will have uncovered a completely new kind of matter, a particle that has no charge, no color, and no weak interaction, only gravity. And that discovery would open the door to something even more profound, a hidden sector of physics, a whole family of particles and forces that exist alongside our familiar world, barely interacting with it, yet shaping the universe on the largest scales. The sterile neutrino may be just the first member of that hidden realm. That hidden realm could contain an entire family of particles and forces, all invisible to our instruments. Physicists call it a hidden sector, a shadow world that barely interacts with the ordinary matter we know. The only bridge between our world and that hidden one might be a new particle called the dark photon. It behaves like a regular photon, the carrier of electromagnetism, but it has a tiny mass and it couples to a different kind of electric charge, one that ordinary particles do not possess. This means the dark photon would only interact with our world through a very weak mixing with the ordinary photon, a kind of quantum trembling that allows it to occasionally convert into a regular photon or absorb one. Why would nature bother with such a particle? Because a hidden sector offers a clean explanation for dark matter. The dark matter particles could be charged under this shadow electromagnetic force, interacting among themselves through the dark photon. but remaining completely invisible to us because they have no ordinary electric charge. This would give dark matter a rich internal structure, allowing it to clump and cool in ways that pure gravitational dark matter cannot. It could also explain the small-scale puzzles of galaxy formation, like why some dwarf galaxies are so diffuse or why the Milky Way has so few satellite galaxies. The hidden sector might even solve the muon G2 anomaly, a stubborn discrepancy between the measured and predicted magnetic moment of the muon. A dark photon with just the right mass and mixing could add a tiny quantum correction that brings theory into line with experiment. Particle accelerators around the world have been hunting for this particle. Experiments at the Large Hadron Collider, the Bell Roman 2 detector in Japan, and dedicated searches like the NA64 experiment at CERN have scanned a wide range of masses and mixing strengths, but so far they have found nothing. That does not mean the idea is wrong. It only means the dark photon may be hiding in regions of parameter space that are harder to reach, perhaps with a very small mixing or a mass that lies outside the current search window. Astronomers have also looked for astrophysical signatures. A dark photon can decay into ordinary particles, producing a faint glow in parts of the spectrum that telescopes can see. Some searchers have targeted the cosmic microwave background, looking for an excess of energy that might come from a decaying dark photon. Others have studied the light from supernova, where a dark photon would carry away energy and alter the explosion. None of these searches have yet produced a clear signal, but the sensitivity is improving every year and the theoretical motivation remains strong. A hidden sector with a dark photon is not just an extension of particle physics. It is a different way of thinking about the universe. Instead of a single set of particles and forces, we may live in a layered cosmos where multiple independent realms coexist, each with its own rules, and only the faintest of connections link them. That layered structure leads directly to the deepest question of all. What is spacetime itself made of? If hidden sectors exist, then the fabric of reality must be far more intricate than a simple, smooth continuum. The geometry that holds both our visible world and an invisible shadow world must be something stranger, something that can accommodate entire hidden universes within the same stretch of space. The structure of spacetime may be the ultimate hidden layer, the foundation on which all other hidden structures rest. Yet the quantum foam may violate one of the most cherished principles in physics. That principle is Lorentz invariance, the idea that the laws of nature look the same to every observer, no matter how fast they are moving. It is a cornerstone of special relativity and the foundation of modern physics. But at the Planck scale, the frothing, grainy structure of spacetime might break that symmetry. If space is made of tiny, discrete units like pixels on a screen, then those pixels define a natural direction, a preferred frame, a kind of cosmic grid that picks out a specific orientation. In such a universe, light and particles would not behave identically in all directions. Their speed would depend on their energy, a phenomenon called modified dispersion relations. A high-energy photon, for example, might travel slightly slower or faster than a low-energy one, a tiny difference that would accumulate over billions of light years. This is exactly what astronomers have searched for using gamma-ray bursts, the most luminous explosions in the universe. When a burst erupts billions of light years away, its photons arrive at Earth over a spread of energies. If Lorentz invariance is broken, the highest energy photons should arrive either earlier or later than the lower energy ones, depending on the sign of the modification. The Fermi Gamma Ray Space Telescope has measured the arrival times of photons from numerous bursts, and so far, the results show no detectable delay within the limits of current instruments. That places a tight constraint on how much Lorentz symmetry can be broken, but it does not rule out the possibility entirely. The effect might be too small for Fermi to see, or it might only appear at energies beyond those we can currently observe. Another search uses ultra-high energy cosmic rays, particles that strike Earth with energies millions of times greater than anything produced in a collider. If Lorentz invariance is broken, those cosmic rays would interact with the cosmic microwave background in unexpected ways, either disappearing too quickly or surviving longer than standard physics predicts. The Pierre Auger Observatory in Argentina has compiled a vast catalogue of these rare events, and the pattern of cosmic ray energies and arrival directions matches standard physics within the current statistical errors. Yet the hunt continues because even a tiny violation would reveal a hidden structure beneath spacetime itself. It would mean the universe has a built-in lattice, a crystalline framework that defines a fundamental sense of direction and speed. If that lattice exists, then the smooth, continuous spacetime we experience is only a low-energy illusion. At the highest energies, reality becomes a crisp, frozen grid, a hidden geometry that dictates the very rules of motion. And that would change everything we think we know about the nature of the cosmos. That crystalline lattice may be spacetime's true nature at its deepest level. The theory of crystalline spacetime proposes that the smooth, continuous fabric we experience is only a low-energy approximation, just as a solid crystal appears smooth until you zoom in to see its atomic grid. At the Planck scale, space itself would be composed of discrete cells, like the atoms of a crystal, arranged in a regular pattern that defines the most fundamental structure of reality. This idea is not as abstract as it sounds. It provides a natural solution to one of the greatest problems in physics, the infinities that plague quantum gravity. In a continuous spacetime, calculations often blow up to infinity because you can divide space into arbitrarily small pieces. But in a crystalline universe, there is a smallest possible length, a built-in cutoff that prevents those infinities from appearing. The equations simply stop at the scale of the crystal cell. This cutoff is not imposed by hand, it emerges naturally from the geometry itself. The crystalline structure also offers a concrete explanation for the holographic principle. In a lattice, the number of possible states is limited by the number of cells on the boundary, just as a screen's resolution is limited by its pixels. The interior of a region of space with all its complexity would be encoded on the surface of that region, exactly as the holographic principle demands. The crystal becomes the physical mechanism behind the hologram. If spacetime is truly crystalline, there should be observable consequences. One is the presence of Planck scale anisotropies, tiny variations in the properties of space depending on direction. Light traveling along one axis of the crystal might behave slightly differently than light traveling along another. These differences would be unimaginably small, but over cosmic distances they could accumulate. The cosmic microwave background, that ancient light from the early universe, would carry a faint pattern of preferred directions like the grain in a piece of wood. Some analyses of the Planck satellite data have hinted at such a pattern, with certain directions in the sky showing slightly different temperatures than others. The signal is weak and controversial, but it has not gone away. Another signature would appear in the propagation of high-energy particles. Just as a crystal can bend light in specific ways depending on its lattice orientation, a crystalline spacetime could cause particles to move at slightly different speeds depending on their energy and direction. Polarized light from distant gamma-ray bursts might arrive with a rotation that cannot be explained by magnetic fields. Astronomers have searched for this effect and placed limits on how strong any crystal-like anisotropy could be. The limits are tight, but they do not yet rule out the idea entirely. This crystalline picture leads to a profound shift in perspective. The universe is not built from fields floating in an empty, featureless void. It is built from a rigid, geometric structure, a framework that predates every particle and every force. That framework may have its own defects, its own dislocations and grain boundaries, just like a real crystal. Those defects could be the seeds of cosmic structures, the first irregularities that grew into galaxies and clusters. And if spacetime is crystalline, then the overall shape of the universe, its topology, becomes a property of the crystal itself. The crystal could be finite or infinite, connected or disconnected, folded or flat. The next hidden structure is not about what fills space, but about the shape of the container itself. The container that holds everything may have a shape stranger than a simple sphere. For centuries, we assumed the universe stretched infinitely in all directions, flat and unbounded. But cosmic topology asks a different question. What if space is finite, curved back on itself like the surface of a colossal torus or the facets of a 12-sided crystal? In such a universe, traveling far enough in one direction would eventually bring you back to where you started, just like walking around the circumference of a planet. The geometry would be multiply connected, meaning that different paths through space lead to the same point. Imagine living inside a vast three-dimensional donut. You could leave your home, fly straight for billions of light years, and eventually approach the same galaxy from the opposite side. That possibility is not just a mathematical curiosity. It is a testable hypothesis because a finite, multiply-connected universe would leave a distinct fingerprint on the light we receive from the sky. The most sensitive probe of this hidden shape is the cosmic microwave background, the ancient glow that fills every direction. If space loops back on itself, then the same patch of the early universe could appear in multiple places on the sky. Light from that single patch would travel along different paths, wrapping around the universe like a thread wound around a spool, and arrive at Earth from separate directions. Those separate images would be identical except for the slight shift in temperature caused by the different journey lengths. Astronomers call these matched circles, pairs of circular patterns in the microwave background that are statistically identical. Finding even one such pair would confirm that the universe has a finite, folded topology. The leading candidate for such a shape is the Poincare dodecahedron, a three-dimensional object made of 12 pentagonal faces that is finite yet has no edge. In this model, the universe would be about 60% of the size of the observable horizon, meaning that the circle matching should be detectable with the right analysis. When the Planck satellite released its full sky maps, several teams searched for matched circles using a variety of algorithms. They looked for pairs of circles with the same temperature pattern over a range of angular sizes and orientations. The results were tantalizing in some early studies, which reported a handful of candidate pairs, but deeper analysis with more advanced statistical methods showed that those candidates were likely coincidences. The null result from Planck placed a strong constraint on how small the universe could be. It ruled out the simplest toroidal shapes smaller than about 90% of the observable horizon. But it did not eliminate the Poincare dodecahedron or other more complex topologies entirely. The search continues with newer data from ground-based telescopes and future missions, each with higher resolution and sensitivity. The shape of the universe is not just a curiosity about geometry. It directly affects the vacuum, the lowest energy state of empty space. In a finite universe, the quantum fields that fill the void are forced to obey the boundary conditions imposed by the topology. They can only vibrate in certain allowed modes, like the standing waves in a pipe closed at both ends. Those restrictions alter the vacuum energy, the mysterious dark energy that drives cosmic acceleration. If the universe is multiply connected, the pattern of that vacuum energy would be subtly different from a flat, infinite universe. Measuring those differences could one day reveal the hidden shape of the cosmos, and with it, the fundamental nature of the vacuum itself. The emptiness of space is not truly empty. A field fills every point, invisible and constant, and it is the reason most particles have mass. This is the Higgs field, a hidden structure that was proposed in the 1960s to solve a deep puzzle in particle physics. Why do the carriers of the weak nuclear force have mass while the photon, the carrier of electromagnetism, has none? The answer lies in a process called spontaneous symmetry breaking. Imagine a perfectly round dinner plate spinning on a stick. The system is symmetric all around until the plate tilts and settles into a stable orientation. That tilt is the symmetry breaking, and it creates a preferred direction out of a symmetric situation. The Higgs field undergoes a similar tilt. In the early universe at extremely high temperatures, the Higgs field was symmetric with zero value everywhere. As the universe cooled, the field settled into a non-zero value that is the same across all of space. That non-zero value is called the vacuum expectation value. Think of a Mexican hat potential, a shape like a sombrero with a central hump and a circular trough at the bottom. The field originally sat on top of the hump, an unstable equilibrium. When it rolled down into the trough, it chose a specific point on the rim. That choice broke the symmetry, and because the field now has a constant, non-zero value everywhere, it interacts with other particles as they move through it. Particles that interact strongly with the Higgs field acquire a large mass, like a person wading through thick mud. Particles that interact weakly get a small mass, like a person walking through thin air. The photon never interacts with the Higgs field at all, so it remains massless. This mechanism explains the masses of the W and Z bosons, the electrons, quarks, and all the other massive particles. The Higgs boson, discovered at the Large Hadron Collider in 2012, is a ripple in this field, a tiny oscillation that confirms the field exists. But the Higgs field also contributes to the vacuum energy, the energy of empty space. Its vacuum expectation value adds a huge amount of energy to the vacuum, far larger than what we observe as dark energy. This is the cosmological constant problem, one of the deepest mysteries in physics. The Higgs field should make the vacuum billions of times more energetic than it actually is. Something is cancelling that energy almost perfectly, and we do not know what. That cancellation could be accidental, or it could point to a hidden mechanism that fine-tunes the vacuum. And the Higgs field has one more disturbing property, the Mexican hat potential that describes it might not be stable forever. There could be a deeper trough, a lower energy state that the Higgs field could tunnel into. If that happens, the vacuum we live in would decay, transforming into a different state with different physical laws. That event would spread at the speed of light, rewriting the fabric of reality as it goes. The possibility of vacuum decay is one of the most dramatic fates the universe could face, and its trigger lies in the very same field that gives us mass. That deeper trough in the Higgs potential could be waiting for a quantum trigger. Our current vacuum, the state of empty space that persists across the universe, might not be the lowest possible energy level. It could be what physicists call a metastable state, like a ball resting in a shallow dimple on a hillside. A small nudge could send it rolling down into a much deeper valley, releasing an enormous amount of energy and transforming the very fabric of reality. This process is called vacuum decay, and it would happen through bubble nucleation. Somewhere in the cosmos, a random quantum fluctuation could create a tiny bubble of the true lower energy vacuum. That bubble would be incredibly small at first, far smaller than an atomic nucleus, but inside it, the laws of physics would be completely different. The masses of particles, the strengths of forces, even the number of dimensions could change, and that bubble would not stay small. The lower energy state is more stable, so the bubble would begin to expand, and it would expand at nearly the speed of light. At its expanding wall, the old vacuum would be converted into the new one, and everything inside the bubble would be annihilated or transformed beyond recognition. Stars, planets, living things, all matter as we know it will be destroyed. Not shattered or burned, but simply replaced by a different kind of existence, one governed by alien rules. The spread of the bubble would be invisible from the outside. We would have no warning until the wall reached us, and then it would be instantaneous. This is not a speculative disaster that could happen tomorrow. The lifetime of our vacuum, if it is metastable, is estimated to be far longer than the current age of the universe, perhaps 10 to the several hundred years. But the fact that it could happen at all reveals a hidden structure of reality that is both fragile and profound. The vacuum we inhabit is not the final, permanent ground of being. It is a temporary arrangement, a metastable plateau that could eventually give way to something else, and that something else might have its own hidden structures, its own particles, its own geometry. If vacuum decay ever occurs, the new bubble would carry within it a completely different set of physical laws, perhaps even a different number of dimensions or a different dark energy. In that sense, the decay is not just destruction. It is a transition to a new phase of the cosmos, a fresh start written in the language of the deeper vacuum. This idea brings us to the very edge of what we can know about the hidden architecture of the universe. The vacuum is not empty. It is a dynamic, potentially unstable layer, and its fate may be written in the same equations that describe the Higgs field. That field, which gives mass to everything we touch, may also hold the key to the ultimate destiny of all structures, including the ones we have not yet discovered. The universe itself may be a single quantum system. Every hidden structure we have explored, the cosmic web, dark matter halos, quantum foam, extra dimensions, the holographic boundary, all of them could be emergent aspects of a single, unified quantum reality. In this view, the separation between an object and its environment is not fundamental. It is a practical simplification, a way we slice the whole to make sense of it. At the deepest level, there is only one quantum state, one wave function that describes everything past, present, future, and all the possibilities that never happened. This idea dissolves the boundary between observer and observed. In standard quantum mechanics, we talk about wave function collapse when a measurement occurs. But if the entire universe is a single quantum system, then who or what does the measuring? There is no outside observer. Some interpretations solve this by saying the wave function never collapses. It simply branches, as in the many worlds interpretation we touched on earlier. Others, like pilot wave theory, propose that every particle has a definite position guided by a hidden wave that extends across the whole universe. That hidden wave or guiding field could be the underlying structure from which all else emerges. Quantum Bayesianism or cubism takes a radically different approach. It treats the wave function not as a real thing but as a tool, a way for an agent to update their beliefs about what they will experience. The hidden structures are then not objective features of the universe but patterns in our expectations. Yet even in that personalist view, the consistency of those expectations across billions of observers points to something rock solid underneath. Entanglement ties this all together. Two particles can be linked so that measuring one instantly determines the state of the other, no matter how far apart they are. This phenomenon is not a violation of relativity, it is a feature of the unified quantum system. The universe itself may be entangled on cosmic scales, a vast network of correlations that connect every galaxy, every particle, every moment. The hidden structures we have catalogued, from the cosmic web to dark energy, may simply be the macroscopic consequences of that entanglement, coarse-grained patterns in a sea of quantum information. This unified picture does not replace earlier theories. It weaves them into a single fabric. The hierarchy problem, the fine-tuning, the identity of dark matter, all of these become different perspectives on the same underlying system, a system whose rules are given by the quantum state and whose evolution is governed by a single equation. We may never observe that state directly, any more than a fish can observe the water it swims in, but we can infer its properties from the patterns we see, the hidden structures that shape our reality. And perhaps that is the ultimate lesson. The universe is not a collection of separate things. It is one thing, one process, one unfolding. The hidden structures are not hidden because they are small or distant. They are hidden because they are the very fabric of the whole, too close and too complete to be seen from the inside. They are the grammar of a language we are still learning to read. And the final sentence, the closing thought of this journey, is that the cosmos may be simpler than we imagine and stranger than we can conceive, a single quantum system whose every part is tied to every other across all of space and time. 30 theories, and yet the universe keeps its deepest secrets close, like a book whose final chapters remain unwritten. From the vast filaments of the cosmic web to the churning quantum foam, from the taut strings of broken symmetry to the shimmering surfaces of a holographic projection, each idea we have explored peels back one more veil. They reveal not a simple cosmos but a layered, interconnected reality, where dark matter halos cradle galaxies and sterile neutrinos drift as silent witnesses. The vacuum itself may be a metastable platform, the Higgs field a fragile bridge to an unimagined foundation, and the entire fabric of space a crystalline lattice or a neural network learning its own rules. Some of these proposals rest on solid math, others on daring speculation, but none have yet been confirmed by a decisive experiment. That is the beautiful tension of science. We hold up these models like lanterns in a vast cavern, hoping one will illuminate the true shape of the walls. The search continues with every gamma ray burst measured, every axion cavity tuned, every gravitational wave detected. And it continues with you, sitting at the edge of your own curiosity, wondering which of these hidden structures might one day become a cornerstone of our understanding. So I will leave you with a question: which theory caught your imagination the most? Did the idea of a crystalline spacetime speak to you, or the possibility that we live inside a simulation? Share your thoughts in the comments below, and if you want to join us on the next journey into the unknown, hit that subscribe button. The universe is still waiting to show us its deepest folds.